Number 2.
I don't know why. Yeah, the little work.
Of a question, if you have a case tomorrow, you have homework that has to be one. Oh yeah, let's do 2.
I don't have any extra homework for that, but look back at your own homework, because that's where it comes from. Thank you.
It's like an optional.
All right. All right, let's talk about what we do. So multiplication comes first, so I'm going to multiply those 2 there, and it looks a bit like an exponent property problem. So first things first, I'm going to multiply the coefficients together to get -16. Then I have x4, x5, which gives me what? x9. And then I have y3 and y2, which gives me y5. What do you notice about these 2 terms now? They're like terms, right? By definition, like terms, same variables, same exponents on those variables. I'm seeing lots of cell phones right now, guys. If y'all will put those away, or else we can start putting them up like third block does. X9, Y5 variables are the same. Exponents are the same. It's the coefficients that differ here. So I'm just going to combine the coefficients. -16 and 7 give me what? -9. And then everything else stays exactly the same. Yes, no, maybe so? Yeah. What else on your homework? 17. Step. That was sad. I just put that piece of gum in. Oh, I went to sing it and it would plop out of my mouth. 17. It's hot in here. Oh, y'all would ask me about this one. I got to do this 3 times. Okay? That's going to be the terrible part about this one. 1 minus 2n, 1 minus 2n. Never, ever, ever distribute when there's a plus or minus inside. Now this one, I can distribute this because like you said, that's just one little term outside. So this would be 7n cubed. Now notice I'm distributing -7n. Thomas, that's not your seat. Swap back. Plus 14n. The minus here goes with the 7.
Oh, because there's 2 minus.
Yep. All right, you can never multiply more than 2 at a time. Boys, switch seats. I'm going to FOIL these 2 out. I get 1. Everybody wants to do that. You talking about go boop, boop? Yeah. Minus 2n plus 4n squared, yeah. Either one's the same thing. You can do it either way. Subtracting and adding a negative, same thing. Can't do that. When you're adding or subtracting inside here.
Because that's like a number in X.
If you're ever adding or subtracting inside parentheses with an exponent out here, that never distributes. But this one is just multiplying one number outside the parentheses so I can distribute that. When you're multiplying, you can distribute, but exponents aren't distribute. All right, so yeah, I'm going to combine like terms minus 4n plus 4n squared. Now remember, I still have this piece here, right? That piece, I don't know why my marker's so big this morning. All this is still here. It's just going to follow this problem down until I'm ready to use it. So now whenever I multiply this through, oh, gross. Okay, so I'm going to take the first one, and it's going to distribute through. 1 times 1 is 1, minus 2n, and I'm done with that one. Go to the next one. Negative 4n times 1. You use each one of them has to distribute through to everything. Well, so now I look at this number, right? It has to distribute through to everything times 1 and times negative 2n. And I still have these little values on the end that I am going to have to combine. Yes, thank you. Sorry. All right. Biggest power I see is 3, so let's grab all those together. Yep. Negative 15n to the third. Now powers of 2. 12n squared. Done with those. N's. I've got negative 4, negative 2, and 14. 8. And then the 1 that's on the end there. What type of polynomial is that? A cubic polynomial because there's 4, right? 20. $20. 16a to the fourth. Remember we talked briefly about division. We didn't go into a lot of detail because I said we're only right now going to be dividing by what? What's that called? A monomial, one term, right? And whenever I'm doing that and I'm adding or subtracting on the top, I can split this up into separate fractions. So this is going to be 16a to the fourth over 12a cubed. I'm doing the backwards of adding fractions with like denominators. Minus 40a squared over 12a cubed plus 24a over 12a. Yes? Now simplify each one using those exact same properties of exponents we've been doing, right? 16 over 12 simplifies to what? 4 over 3, and then I've got 4 a's up top and 3 in the bottom, which leaves me 1a on top. Minus 40 over 12 simplifies to what? 10 over 3. And then what is 1a on the bottom? That would be 2 with 2 a's on the bottom. Now, if you wanted to... Yep, sorry. Oh, this is a 1, this is a 1, this is a 1. Sorry. There's nothing there. It's 2. There you go. Sorry. Bro, it's been a morning. Yeah, that's it. That's all I can do. Does that make sense? Sorry. I threw everybody off. That's the final answer. It has been buzz for me so far. Like I need a shot of espresso or something. I can't keep up. I probably need something to calm me down. All right. What else on your homework? Huh? 21 and 22. Are you gonna have what? Possibly. Probably. I'm trying to start y'all early with some word problems because calculus is complaining every single day that they don't know how to interpret a word problem. So I figured the earlier I start you, then. All right, 21. The length, width, and height of a rectangular prism can be represented by. Ooh, I see why y'all didn't like this. Yeah. So surface area is the area of each face added together. And it's a rectangle, right? So if you think about a rectangular box, what? Oh, right. But they're not all the same, right? So this says I have, all right, length. So this is x plus 3. The width, that's height. So here, x plus 7. And then the height is x minus 1. So let's think about what these, how do I find area, by the way? That's volume. Length times width, right? So each one of these, I'm going to do length times width on. So here I've got, so for this front, right? And if you think about it, the front and the back are going to be the same, right? So 2 of these, and it's x minus 1 times x plus 3. Agree or disagree? That's just this very front face and the back face, okay? Now let's do the top and the bottom. They should be the same because it's a rectangle, right? So 2 of these, and it's x plus 7 and x plus 3. And now the 2 end caps here, right? X minus 1, and there's 2 of them again. Zoom out a bit. X minus 1, x plus 7. That's surface area. Well, it didn't tell me to simplify it. It didn't tell me to write a polynomial in standard form or any of the sort. This is definitely an expression. I would say the directions were vague and that they probably did want you to multiply it out and simplify it and find a polynomial, but since they did not say that, I would stop there and say, that is an expression, the correct expression. If y'all want me to multiply it out, I surely will. Huh? I mean, I'm going to do just what they asked me to do. That's one thing I harp on in calculus all the time. Don't do more than you have to do. Work smarter, not harder, right? Yeah, no. Okay. All right. You got that? The area of a triangle. I always have to draw a picture. I'm the world's worst artist, but this is my height, and my base would stretch all the way across, right? I know I need that because how do you find the area of a triangle? 1/2 base times height, right? All right, so I want the area of a triangle can be represented by the expression. So now they're telling me what area is. They say area is 14x to the 5th plus 63x squared. If the base, so this is area, if the base is 7x squared, what's its height? We'll plug in what you know. Look, we know A and we know B. Here's A and here's B, excuse me. So let's just plug in what we know. A is going to be 14x to the 5th plus 63x squared. 1/2, what's the base? 7x squared times, I don't know the height, that's what they want me to find. They said, that's exactly right. I need to know what h equals because it says an expression for the height. So I can't stop here this time because it says I need to know what the height is. So my question to you is, how do I get h by itself? Divide by what? Okay. So yes, the first thing I'm going to do though, I'm going to multiply by 2 so I don't end up with a fraction in the bottom. Okay. I'm just going to take care of that first. You could technically move everything at the same time. So I'm going to have 2 14x to the 5th plus 63x squared. Now let's go ahead and divide that 7x squared. And again, unless they tell me to simplify or they tell me to write it as a polynomial in standard form, I'm just going to leave it just like that. Even though this will simplify nicely, I don't care because I did what they told me to do. This will, you will see whenever we get to the further lessons, not today, but past today. There's lots of practice. Possibly. Yeah. Maybe. I know. All right, let's switch gears. Yes, today is very analytical. We are analyzing graphs. Definitely, oh, all the calculators are out, huh? When we finish with polynomial analysis over the course of this unit, you will have probably anywhere from 8 to 12 steps in the analysis. Today we're going to talk like 3 of them. Yeah. I am 3/4 of the way through, so yes, to answer your question, yes, I'm almost through. Before report cards, absolutely. Approved? You never do proofs again until you get to super, super high level. No, I'm talking like college level. Like, I didn't either. I went as a math major. And it wasn't until further on in my... All right, ready, Freddies? All right, we're going to talk today let me just mention this. We talked briefly about classifying polynomials by their degree. We said a degree of 0 was a constant. What does that graph look like, though? What does the graph of a constant look like? Huh? Straight line, this way, right? It looks just like this. Okay? If I go up a degree, and I say the degree is 1, what's that type? What did we say that was? That's linear, right? What does the graph of linear polynomial look like? It could look like this, or it could look like this, and we're going to talk about what makes that happen. You already know what makes that happen, though. What makes it flip? The negative. That's exactly right. The negative in front would make it flip. If we increase the degree by 1, we end up with a what? A quadratic. And what does a quadratic look like? A parabola. And it too could open up, or it could open down. And what determines which way it opens? The negative in front, the leading coefficient, right? That's very important, and we're going to get that. I'm going to keep stressing that. It's that leading coefficient. And then a degree of 3 is called a what? A cubic. And a cubic, if you don't know, could look like this, or like this. Now, sometimes these are more stretched out, the humps are pronounced, sometimes they're not. That's irrational. We won't get to that for quite a while.
Good morning.
All right. Yeah, we'll get irrationals a long time from now. All right, let's do degree of 4. What is it? Corte. Spanish. What do you notice is happening? I get another loop every time I add a degree, right? And that happens now. Don't think if you just graph the parent graph, like for instance, if you just graph y equals x cubed, you're going to get something that looks like this. The humps aren't really pronounced here. As you start doing manipulations with it, these humps will come back out. But I just show you this so you can see what happens if we start adding degrees to it. And we're going to talk about some patterns that start emerging in these polynomials. Okay. Alrighty, y'all ready for the good stuff? That was kind of a little recap. It would just keep, so a degree of 5, yeah. You're so smart, that's what we're talking about. Yes, that is an excellent observation. Say it again though, Lane, say it again because that's what we're leading into. Who did it? That was awesome. Who is that? That's cool. Harris? Okay. When the degree, Lane said when the degree is even, the arrows are going the same way. And when the degree is odd, the arrows are going in opposite directions. And that is an awesome observation because that is exactly right. But, okay. What? Okay, so let me show you and then I'll explain what she's saying. If I did quintic, I have to think about it there. Or, that's a, you don't have to, just, that's a 5, yeah. Every time I add a degree, I add another potential hump here. Okay, we'll talk about what this hump it does, I know. But excellent observation there because that's what we're going to use to define in behavior. So, in fact, let's write that down. If the degree is even, we know that either both of them go up or both of them go down, right? They go in the same direction. We said a quartic looks like that. Oops, Stacy. And so on and so forth. And if I kept going, I would notice the same thing, that both ends go in the same direction, no matter which way, if it's going up or down. If that degree is even, they're going the same way. And then on the other end of that is an odd degree. Which goes in, oh no, opposite directions. Need to borrow one? The hardest part about what I'm fixing to show you is the notation itself, okay? We've got 2 things to talk about today. This is the easy part. Both of them up or both of them down? No, not today. Yeah, you'll see where this ties back in. If you don't quite make the connection. Paris. Yeah. Let's talk about in behavior. Didn't I just fix that? Oh, Harris. All right, so in behavior. In behavior does exactly what it sounds like it does. It tells me what the end of the graph is doing. Okay? So I'm going to teach you a little math lingo here. You ready? How many ends of a graph does a polynomial have? 2, right? I've got 2. Either both going up, both going down, or opposite directions, but there's always 2. Do we agree? We're talking about polynomials. We're not talking about the one where y'all were asking about the ones that approach the asymptotes or whatever. We will get to that. It doesn't end, but we want to talk about what happens in the infinite side where it goes on forever. So we call it end behavior. That's exactly. Have y'all done that before? Did we do it in here? Oh. Dang, y'all did that already for real? Okay. 2 ends to a graph. 2 ends to a graph. I'm going to start with just a plain old line because we all understand a plain old line. As I use this as an example to describe in behavior, okay? Here's what we're going to do. As X, and then I'm going to use this little arrow. That little arrow means approaches. And you'll see what. Not yet. We're fixing to get to calculation. As X approaches infinity. Now let's stop right there for just a second. I'm talking about X approaching, and I say approaching because it can't actually equal infinity, right? That's the concept of conceptual thing. As I approach infinity, so as I move towards infinity, well, which direction does X move towards infinity? Which way? Left to right? Which one? Right, right? From the left to the right, yes? All right, so this is telling me, if I'm talking about X approaches infinity, this means the right end of the graph. Okay, that says look to the right. Does it make sense why that says look to the right? X gets bigger to the right. Then f of x, which f of x is the same thing as what? Y. Then f of x approaches, well, look at this graph, look at this line. As I go to the right, what is the graph doing? It's going up. Do we all agree? How do you say y goes up, or how do you think you might say y goes up? Infinity, positive infinity, okay? So f of x to infinity means up. It kind of ties in, absolutely. It does kind of tie in. Now, I told you the end behavior, and you told me there are two ends, yes? So how about the other end? Up. No, you're good. All right, as x approaches negative infinity, which tells me what? Look to the left. What is the graph doing? Going down. How do you think I'm going to say down? Negative infinity. So f of x to negative infinity means down. These are your four key little phrases that you will use over and over. And in fact, as we describe the end behavior of polynomials, when I ask you what's the end behavior, there's always two mathematical sentences. This is sentence one, this is sentence two. They are always exactly the same up until I get to that last infinity. That's the only thing that's changing each time, is me determining is it going up or down. Why are y'all doing that? What's circled in green never changes. It's what's on the end of those that changes. So let me give you an example of another graph, and I want you to describe the end behavior for me. Ready? And instead of giving you the graph, I'm going to give you an equation. Yes, Harris? No. One time, really quick. I'll leave it on if you don't abuse it. Describe the end behavior of the graph. Don't actually graph it. Look at it, think about it, about what you know about this graph, and describe the end behavior. You don't know anything about it? It's a quadratic, right? And it's negative, so it's going to go down. So it's going to be something like this. I'm not worried about where on the graph it is. I'm not worried about stretches, strength, anything else, because in behavior, all I need to know is what the ends are doing. Now describe the end behavior. You take a minute to try it, and then we'll do it. The end behavior. And in fact, because we know all end behaviors consist of two sentences that are exactly the same other than that very last value, I can write that out. That's the first part every single time on every one of these. I got to determine if it's positive or negative. It doesn't. So what does this first sentence say? As x approaches infinity. So as I look to the right, what's the graph doing? It's going down. That's this end right here. So down is negative infinity. As I look to the left, down. Now, in fact, if we use what conclusion she came to earlier, and we kind of think about this, we can know the end behavior for any polynomial in the whole wide world if we only know its degree and if its leading coefficient is positive or negative, right? The positive or negative in front determines up or down, and the leading the degree determines if they're both going the same way or if they're going opposite. So let's think about this for just a minute. This is a very important chart. You'll want to put this someplace very important in your notes. Let's say that this is even on the top row, but the leading coefficient goes positive and then negative. I'm just going to have end behavior written below each one of these. So 2 more lines under this for each one. Degree is odd. And leading coefficient positive. Negative. So if we can derive this little chart, then we can have a little cheat sheet of any end behavior of any polynomial in the whole wide world without actually having to graph it or think any further about it, just by looking at the degree and the leading coefficient. Leading coefficient. Remember the negatives, this just means that they're flipped upside down from what you would normally see, right? That's all that it means. Now, let's do the evens first because the evens are the easiest in my opinion because we know evens both go in the same direction, yes? So remember all of these sentences are going to start the exact same way. So you could even go through each one of these and fill out everything except that very last infinity. I used to make students do this on a colored paper, but I found that you start using it as a crutch too much, and it's really pretty easy to think about to make that connection between what's going on. Yeah. His mind is blown. All right, if my degree is even, so up top, that very first row, both ends are going in the same direction, yes? Do we all agree? Quadratics, quartics, powers of 6, 8, 10, so on and so forth. It doesn't matter what in the world is happening in the middle. I know both ends are going to go the same direction. And what determines that direction? The leading coefficient. If it's positive, both ends are going what? Up, right? So here, both ends are going up. What happens if it's negative leading coefficient? Both ends are going down. That's exactly right. I'm so proud of y'all. This is the first group that I've had this derive this on their own. That was smart. Do I? You'll understand. All right, how about the bottom row? I've got odd degree, so that means I'm going in opposite directions. So I have to think about, am I going this way or this way? So I always think about a line because it's the easiest, most basic odd degree that I can think of, right? And I think about a line with a positive slope because that would be a positive leading coefficient. And then I think about a line with a negative slope because that would be a negative leading coefficient, yes? Even just one example that fits these criteria will give me enough information to figure out the end behavior. So looking at the first square here, as x approaches infinity, what's the graph doing? This way. What's the graph doing on the right? Did y'all say it? I'm sorry. It's going up. That's positive infinity. Here's the right. Now on the left, what's the graph doing? Down. How about the one on the right? Down. To the right goes down, and to the left goes up. Yep, just swaps. Yep. Oh, good. I got one more thing to show you. I got to show you the calculator thing. I hope y'all have done it before. If you haven't, oh dear goodness. What? Oh, yeah. Absolutely, I agree 100%. Describe that polynomial. No, just tell me first, what is it? It's a what way? It's a 15th degree. It's a 15th degree trinomial. Well, the n is whatever degree it is. So if it's, yeah, sorry, I should have said that. If the degree is, yeah. Now, that's it's 15th degree trinomial. That is a crazy polynomial, yes? Describe the end behavior. Tell me what the ends are doing. I don't care what the inside's doing. It can be doing what I just want to know what the ends are doing. We know it's opposite, and we know that's right. As x approaches infinity, remember, if you're ever asked for end behavior, you always start right this much because you know the two sentences. You know that the only thing that's changing is what's happening on those ends. So on the right end, what is happening? Down. Right? And then up. Now, if I didn't know that here, I could look, okay, well, this is odd and negative. So I could go to my chart. Odd negative is this. So here's my end behavior. Does that make sense? I know.